So here's the left factory grammar now typed out neatly. And we use this grammar to construct a parsing table. And let's not worry right now about how we got this table. I'm not going to give the algorithm right now. But let's just say that we got it somehow. And what I'm going to explain is how we use the table. So one dimension of the table is the current leftmost non-terminal in the parse tree. So that's on the rows. And then the columns represent the next input token. So the next token in the input stream. And then the entry is the right-hand side of the production to use. So which production that we should use at that point in the parse. That's the production that's predicted. So let's do an example. So let's look at the eInt entry. So this entry right here. And what this says is that when the current non-terminal is e, meaning the leftmost non-terminal in the parse tree, and the next input is int, the thing that we see coming up in the input is an integer, then we should use the production e goes to tx. So we should expand e with the children tx. Let's do another example. So when the current non-terminal is y, and the current token, the current input is plus, then we should use the production y goes to epsilon. Okay, what that says is, it's a little bit different situation than the previous one. It says, look, when you see a plus in the input and your current leftmost non-terminal is y, the only way this parse is going to succeed is if the y doesn't produce anything. You need to get rid of the y and move on to another non-terminal, whichever one is leftmost after you get rid of the y, if you want to have any hope of parsing this particular string. And finally, notice that a lot of the entries are blank, and those are error entries. So let's take a look at the E star entry. That says that if the leftmost non-terminal is E, and the next input token is a times symbol, a star, well, then there is no move that you can make. There is no production you can use for E that's going to successfully parse that input. And this is the point at which you would raise a parsing error. In the rest of this video, I'm going to give the algorithm for parsing using a parsing table, and then in future videos, we'll explain how to construct a parsing table. So the method for parsing using a parsing table is similar to recursive descent, except that for the leftmost non-terminal S in the tree, we look at the next input token A. And then, as we just illustrated with the examples, we look up in the table the production to use at the entry S, comma A. And instead of using recursive functions to trace out the parse tree, we're going to have a stack of records that can record the frontier. And so at any point in the parse tree, we will have some non-terminals that have yet to be expanded. Those are always at the frontier, at the current leaves of the parse tree. And also there are some terminals that we have yet to match against. And those will all be recorded on a stack. And the important property of the stack is that the leftmost pending terminal or non-terminal is always at the top of the stack. So either the terminal we're trying to match or the non-terminal we're trying to expand will always be on top of our stack. We'll reject if we reach an error state. So if we look up one of those empty entries in the table, we will reject the string. And we'll accept if we reach the end of the input and we have an empty stack, meaning we have no pending unmatched terminals or unexpanded non-terminals. So here's the algorithm. We initialize the stack to just the start symbol S and the special symbol $sign. And $sign is not part of the alphabet, or you could think of it, we extend whatever our alphabet is with a new symbol called $sign. $sign marks the bottom of the stack, and you can think of it also as marking the end of input. So this is just a way of recording where the end of the input is going to be. Okay, so once we've matched something against S, then whatever is left had better be at the end of the input. That's what that stack expresses. And now we're in a loop, so we're going to repeat the following moves until we can't repeat them anymore, until the stack is empty. Okay? And there's two possible moves. Let's do the terminals first. So let's say the top of our stack is a terminal. So here we're dividing the stack into the top of the stack and the rest of the stack. So what are we going to do if the top of the stack is a terminal? Well, we're going to try to match the input. So we're going to say, well, at the top of the stack, the terminal on top of the stack matches the next thing in the input. Then we advance the input, and we pop the stack. So we have successfully matched the input against the terminal, and so that terminal is done, and we should progress into the stack and match the next thing that hasn't been handled yet. And if they don't match, if the terminal that we're looking at doesn't match the next thing in the input, well, that's an error. We don't have any backtracking here. There's no way to parse the string, and so we'll raise an error. Now, the second class of moves deals with the non-terminal. So let's say that the top of the stack is a non-terminal x. And remember that the top of the stack will be a non-terminal exactly when that is the leftmost non-terminal. So now what we do is we look at our parsing table under the entry for x and the next input symbol, and that should give us the right-hand side of a production. Okay? And now what we do is we pop x off the stack, and we push the children of x in the parse tree onto the stack. So this is the way we expand x. So now the leftmost unhandled thing in the parse is going to be y1, because that's the first child of x. And then all the other children of x are next, and then whatever else is in the stack. And again, if there's no entry for the current non-terminal and input in the table, then that's an error, and the parsing stops. So let's work through an example using our parsing table. And you might want to refer back to the parsing table. I have not included it here because there isn't space for it. But I'll work through it, and you can go back and look at it at some point and convince yourself that I made the right moves. So initially, our stack is $E$. So E was our start symbol, and $ is our end of input symbol. And our input, we're going to try to parse the input int times int. That's what we want to parse. And then, of course, we have our new symbol $. We'll tack that on to the end of the input. And if all goes well, the $sign on the stack will match up against the $sign at the end of the input. Again, $sign here is just a way of marking the end of the input and expressing that we need to parse the entire input. And so now, if you look up the E int entry, so the first terminal in the next terminal in the input and the leftmost non-terminal in our parse, you will see that the action we're supposed to take is to use the production E goes to TX. And let me over here at the same time construct our parse tree. Okay, so initially our stack, again, the stack is the frontier of the parse tree. Initially, all we have is the root of the parse tree, and that is its own frontier. It's just one symbol. We haven't processed it yet. And so E is on the stack. E is unexpanded in the parse tree, and now we're going to use the production E goes to TX. So we'll have T and X added as children. What happens next? Well, E is popped off the stack. T and X are pushed onto the stack. And now notice, the frontier of the parse tree is TX. These are the unprocessed leaves, either unmatched input or unexpanded non-terminals. And in fact, the stack records exactly which one is leftmost. So T is at the top of the stack, X is below it on the stack. Okay, well, we still haven't consumed any input. And now if we look at the T int entry, it says to use T goes to int Y. And so now we can expand T by int Y. And now what's going to happen is T is popped off the stack, int and Y are pushed onto the stack, and now notice the stack is int YX from top to bottom. The frontier of the parse tree is int YX. Okay? And now we have a case where we have a terminal on top of the stack, and so now we're going to try to match it against the first terminal in the input. And indeed they match, and so what happens is int is popped off the stack, and the terminal, the input pointer advances in the input. And here I've recorded that by just discarding the portion of the input that we've processed. So now we have times an int left to go, and the int has been removed from the stack. And so now what's on top of the stack is Y. Y is indeed the leftmost unprocessed thing on the frontier. And the table says that for non-terminal Y, on input times, we should use production Y goes to times T. So let's put that in here. And now what's going to happen, Y is going to be popped off the stack, times T is going to be pushed onto the stack, and now notice our stack is times TX, and the frontier, the unprocessed frontier of the parse tree is times TX. Okay? So now we have a terminal on top of the stack. It matches the next terminal in the input. So we pop the terminal off the stack. We advance the input pointer. Now we have t as our leftmost non-terminal. Int is the next thing in the input stream. And the table says, well, in this situation, we should use the production t goes to int y. What does that mean? That means t gets popped off the stack, int and y get pushed onto the stack. Notice that the stack is int yx, and the unprocessed frontier of the parse tree from left to right is int yx. Once again, we have a terminal on top of the stack. We match it against the next terminal in the input stream. They match. And now we have consumed all the input. $sign is the only thing left to go in the input, but our stack is not empty. Okay, and so at this point, what does that mean? Well, if the stack is not empty and we're out of input, then everything that's left on the stack had better generate the empty string. So we better be using only epsilon productions from here on out. And indeed, the table says that when y is our next non-terminal and $sign, we're at the end of the input, we should use the production y goes to epsilon. So y goes to epsilon, that means y just gets popped off the stack. Epsilon gets pushed on the stack. Epsilon is the empty string, so nothing gets pushed on the stack. And now we're down to x. And in the situation where x is the next non-terminal, $sign is, we're at the end of the input, so $sign is our next symbol. Then the table also says to use the production x goes to epsilon. And then what happens? Well, x gets popped off the stack and nothing gets pushed on because the production was x goes to the empty string. And now we see we have $sign on top of the stack, $sign in the input, and so we have emptied the stack, we have reached the end of the input, and so we accept. That is a successful parse.